Well, welcome everyone, and thank you for joining us today for this ORION webinar series on digital twins for renewable energy operations. We have a great lineup of speakers today, and this is going to be the agenda for today. We'll have an introduction session done by Stine from SINTEF, who is project coordinator, and then we'll have a lineup of speakers who will provide their expertise, and then we'll have the Q&A sessions in the last 15 minutes of the hour. Okay.
Thank you. I am, as Josipa said, Stine Wilhelmine Holm, and I work in SINTEF, one of Europe's largest independent research organization situated in Norway, and I am the coordinator of the ORION project. I am happy to welcome you all to this first out of 4 webinars in ORION webinar series. And the webinars are part of the Sustainable Energy Days, which are events held during the European Sustainable Energy Week, where the goal is to raise awareness and promote clean energy initiatives. The theme for today's webinar is digital twins for renewable energy operations. Can I just move to the next? Yeah. Well, I will start by a short presentation of the ORION project. It's a 3-year research and innovation action, started in September 2024, and lasts until the 31st of August 2027. The budget is 3 million euros, and we are 14 partners from 9 different countries, spread over 4 continents. This slide shows the concept of the ORION project. We have 5 breakthrough components in the project. They are the sensor technologies, the data models and models interoperability, asset management, data-driven decision systems, and finally the human-centric digital twin. In ORION, the digital twin will integrate the digital components and then empower better informed decision-making of the stakeholders, including policymakers, allowing them to share insights in a collaborative and virtual environment. This will help to address the energy stakeholders' need in a comprehensive manner and will include the latest knowledge and best practices from the existing EU platforms initiatives like EnerShare, GaiaX, and FireWare. The modular toolbox of digital breakthrough components will be tested and validated in the 5 use cases of the project. We have the Cape Verde/Norwegian use case, which is on decarbonisation of port cities. We have the Iberian use case on operation and maintenance of large PV farms. We will hear more about these 2 use cases today. The Slovenian use case on operations and maintenance on floating offshore wave energy converters. The Brazilian use case on distributed co-simulations infrastructure connecting real-time simulation in support of digital twin. And finally, the Canadian use case focusing on modeling, monitoring, and reliable operations of energy generation and power electricity systems in Canada. Today's speakers are Scott Young from Augment City. He will talk about the digital twin concepts and how interactive platforms support better decision making. Then Maria Inês Marques from EDP R&D will tell us about operational insights from real-world PV plant integration. Andreas Amundsen from the municipality of Ålesund in Norway will share the lessons from the Ålesund port city decarbonisation journey. And finally, we will hear from Professor Juan M. Escaño from the University of Seville. He is from our sister project Interest, and he will talk about the optimal twinning in the Interest project. And after the presentations, we will have time for a Q&A. So I will by this give the word to Scott Young from Augment City.
Thanks, Dana. Let's see if we can take control here. Okay, so as Tim said, my name's Scott Young. I'm Head of Research and Design at Auckland City, and Auckland City is responsible for the graphical digital twin element of ORION. As Tina mentioned, we have 6 use cases. So Cabo Verde and Norway. Cabo Verde is interested in port energy consumption, and Norway is interested in cruise ship energy consumption. And both of those together is essentially the usage. For Iberia and Slovenia, Iberia is the photovoltaics, and Slovenia is the wave generation. So we're looking at generation. And then for Brazil and Canada, we're talking about power grids and energy plants. So we're looking at grids and systems. So we can break the 6 use cases into 3 broad categories. So from our point of view, and for ORION in general, the GTT acts as a hub, and it brings science and business together. And in this case, for ORION, we look at energy use cases so that the public and the local government can all come together in one meeting point to discuss and look at ideas and problems and communicate more easily to each other. And communication is so important. So with all those use cases, we take their data and bring them into the graphical digital twin, and we then transpose that to the citizens and stakeholders. In the past, that's been kind of one direction. You would present your information, and that information would just be presented to citizens, and then that's it. You would get no feedback. And what we try to do in Auckland City and ORION is we try to gather that feedback from citizens to input back into the graphical digital twin, which then feeds back into the use case. And ideally, we have this positive feedback loop. So for the use case, so the slide's slightly wrong here. What we normally do is we start with a technical focus, and with that technical focus, which is all the kind of data input, etc., which goes into the graphical digital twin, we also try to use what we call a graphical digital twin end user story. In that end user story, what we try to do is understand those who are going to be using the graphical digital twin, and that'll be our partners, when they're communicating with stakeholders, what they want to use the digital twin for. And so it's very important to take this very technical aspect and all this data, etc., and then understand what the end user will use it for, and then bring that knowledge in both of those viewpoints together into the digital twin. So there's a kind of unified experience when presenting, and also that the information is there in the digital twin to communicate. So one of the use cases, like I mentioned, was Cabo Verde. Here we have an animation on the right-hand side of Mandelo, the new port facilities. This is the new cruise ship terminus, and a picture of one of the cruise ships in the top left-hand corner. And here we're trying to look at real-time energy usage for technical buildings. So we're taking that end-user story and the digital twin starting point, and we started mocking up exactly how Mandelo would like to use the digital twin. So we get an understanding of what it is they're looking for. With the Iberian use case, and we'll hear a little bit more next, we're looking at photovoltaics, and it's a lot of it's to do with the fault detection. So as you can see in the image on the left-hand side, we've got kind of remote, very large areas, and trying to get an overview very quickly of different fault detections. And that's what we're trying to kind of diagnose anomalies very quickly here. So you can move on this. And here's an example of a mock-up that we've done to show those strings of photovoltaics, how they may look with fault detection with kind of these large lollipops. So you have a quick overview and a marker. For Slovenia, it's wave detection. So they're doing a lot of information, and they're doing a lot of experimentation in the lab. And you can see on the left-hand side, they're using those lab results to try and transpose those into the real world to understand what's going to be happening in the future. So here we're flying around a potential wave farm off the coast of Norway, and we can see the various machines. And what is important for them is also fault detection. Again, how do you quickly communicate which machines are faulty, which ones aren't? And so again, we're using the lollipop idea from Iberia and transposing that onto Slovenia. And then lastly, at Brazil, we're looking at the wave generation. Here we have these wind turbines, and our tool allows people to very quickly copy and paste these wind turbines, and they can have a site and have wind turbine models, and they can place those wherever they need them. And so they can look at and plan out wind farms as when they need it, which is very important when they're discussing about the visual impact on wind farms, and also then how do they access those through roads, etc. So essentially, that's just a quick overview of what we do in the digital twin. Thank you.
Okay, next we have is Inês, who will take the floor now.
Hello, so I'm Inês from EDP R&D, and EDP is a company from EDP Group that is specially dedicated to research and development. And I'm going to present you the operational insights from real-world PV plant integration. Introducing EDP, we are an integrated electric utility in Iberia and Brazil. We are a renewables developer and operator, and we have a strong presence in the United States and Europe. And through EDP Renewables, we manage a massive global renewable fleet, and from which around 18 gigawatts are from wind and solar sources only. So today we are going to talk about our use case, the PV case, and this is about solar sources, so that's why I introduced it. So how to maximize renewable assets management from a global fleet of these kinds? Specifically addressing the typical challenges of managing a PV park, the focus has always been on reducing the operation and maintenance costs, as well improving monitoring and fault detection and maximizing the PV park availability. And all of this by using AI to support decision-making and fostering operations. And actually, today, many O&M decisions are already being supported by AI and advanced data models. But with research and innovation, we are now opening new ways to address the typical challenges of managing these PV parks. And focusing on research and innovation, EDP is following different domains, and for each of them, we have one or more R&D projects chasing this domain. I will highlight here the ORION project because we are presenting that today. And an R&D project like ORION is developing and integrating digital components for the renewable energy value chain, like digital twins, AI and advanced data models, and other modular digital tools. And that can be implemented in EDP business, for example, through a digital twin with embedded large language models, and that to generate human-like texts to support the O&M operators and other users. And this is the way we are implementing innovation, starting with R&D projects like this one, ORION, leading to the identification of early business opportunities and the innovation development, and making the technology mature to be implemented in the company's business and commercialized. So the objective is to innovate the digital tools used for PV power plants operation and maintenance, having the goal of increasing the operational reliability and efficiency. Following on the idea of transforming data in business value, digital twins can be implemented as a central piece of an AI strategy in PV parks, for example, to maximize energy production, to reduce OPEX. And by creating an exact and visual virtual replica of the physical assets, we can have added value. Using the digital twins to support decision, we can foster the O&M activities, making them more intelligent and digitally and data-driven. We know these activities will be supported by robots. We already have a few implementation cases that are adapted to perform tasks of inspection, surveillance, maintenance, and this can reduce the high costs and reduce the human risks of these activities. And we know as well that today we are having less and less human available to perform the management activities, and this is a case of labor scarcity. So digital twin is not just a dashboard, it is an intelligent operational layer that helps predict issues and recommend actions to optimize performance across the asset lifecycle. Leading us to the ORION project. This project is allowing us to develop innovative digital components integrated into a digital twin structure, and then applying these developments into operations through the implementation of use cases across 4 continents, as already said. And leading us to our use case, the Iberian use case, that is developing advanced and predictive O&M tools for PV parks. Our goal is to enhance the digital twin model, and this is a project objective, and a specific use case objective is to autonomously identify anomalies and fault diagnosis. And through the developments of our use case, we are improving the digital twin to simulate and diagnose anomalies, the fault classification model for the elements of the PV plant, like the strings, inverters, transformer, PV panels, and all the PV plant as a whole, and using AI to support techno-economic decisions and when to perform the O&M activities that will lead us to a high return on investment. In the end, we'll test and validate the models EDPR PV plants. So the ORION digital twin will have a specific scenario for the Iberian use case, and this will receive the results from the models and algorithms being developed in this use case. The algorithms for fault detection, identification, like we have said, the large language models being integrated into the digital twin for the contextual analysis, recommendations, and the operational decision support, and the return on investment models and strategies that will lead us to identify the best timing that minimizes the LCOE and maximizes the return on investment. Oh, I'm sorry, this one should have a different format, so I'm trying to explain this better. And this is about the data that is that we usually identify as useful to visualize in a PV park at a digital twin from a PV park. And this is generally the geographical data, the physical and mechanical properties of the PV park and components, the electrical design and layouts of the PV park, the component specification, weather data, and other operational data. And of course, the results we are getting from the use case development as these algorithms outputs will be inputs in the digital twin. And to visualize this data, the user should have the possibility to visualize the aggregated and disaggregated information for a specific time interval, for example, hourly, daily, monthly, or for a specific component of the PV park, the panel, string, the inverter or transformer. And since we are dealing here with a high volume of data that can be heavy to compute, we need to have in mind the right balance between the details and definition and the computational efficiency. There's no use on having too much information and not being able to see that. So always having that in mind. And having the potential to reach the operational intelligence that helps predict issues and recommend actions and optimize the performance across the asset lifecycle. The information available as an output from digital twin would be useful for monitoring, forecasting, for the maintenance optimization, and for reporting. That will lead us to help on the decisioning process. And now this brings us to the beginning of the presentation, where we introduced the need for solving the typical challenges of a PV park. And today, digital twins are often used to visualize assets and operational data. But we are taking the step to the next evolution, that is making them more intelligent and combining real-time data, for example, or with AI models, weather forecasts, operational historical data. The digital twin can help us to understand not only what is happening, but what is going to happen next and what's the next action that should be taken. This way, selected decisions can become automated, having in mind, of course, cybersecurity and governance. Thank you, and I'm available to respond to your questions in the Q&A session.
Thank you, Inês. Up next, we have Ålesund case studies, and it will be explained by Andreas. You can take the control.
Thank you very much. I will say a little bit about the case in Ålesund, Norway, from an end user perspective, and this perspective being the municipality. I also represent the development company that is developing this pilot site that I will show now. So I will say something about the pilot area and the key challenges we have, but also a little bit about the national situation in Norway and the role of the municipality and how we have developed the case together with Ålesund City. And finally, I will say a little bit about the potential of digital twins and how we use it today. So Ålesund is situated in the west of Norway, and here we have a typical harbor transformation project, which is quite a large area of the center of the city, which has been used for harbor activities, but is now being transformed into housing and other kinds of properties. So today it's a fairly gray area with quite few buildings, and it's not the only one of these transformation projects in the center of the city. We actually have two others. So in this project, we are including quite a large section of the central parts of the city. But today it looks like this. It's gray parking lots, and it's sort of in the middle of a transformation activity. But we are trying to fill it with activities. So this is the situation today, where we are using this site to demonstrate how it will look in the future. So we're using lots of temporary activities to activate the site. Next slide, please. Yeah, so in this project, the sort of main challenge that we are looking at that has come about in the last few years is that while this site was planned to be transformed and have a few cruise ships, this activity has taken over quite drastically because, of course, these ships have grown in size and the need for energy have increased. So if you go one step forward, Scott. Yeah, so one of these cruise ships requires about between 6 to 16 megawatts of shore power, which completely dominates the energy demand for this area. So this is a new challenge for the municipality and also something we have not really planned for. It has just happened. Next slide, please. And if we look into the energy demands in Norway, you can just move ahead a couple of steps to show the text. Yeah, so the Norwegian power production is between 7 and 28 megawatts during the year. And in Norway, our largest single consumer is aluminium production. It's about 700 megawatts, which is a lot. And next, yeah, and now we are getting the new data centers, which are at the same kind of scale. They are consuming maybe 4 to 5% of the national production. So this is a lot. And on the other side, we are producing some energy from wind turbines, but this is on a fairly low scale. And if we compare it to the consumption that we're getting from land shore power, it's not a lot. So next slide, please. Yeah, so this is actually something which has been, it hasn't had that much focus in Norway, but it's coming now. In Norway, we are used to having abundant energy, and we don't really have plans for this at a larger scale. So today we have this queue of data centers that actually require about 1.5 times the consumption of all private consumers, which is, again, a very high number. And for us in the municipalities, the crucial thing in this project is that we do not have a lot of legal tools to control this or plan, and we do not have a lot of decision support for municipalities. So how do we prioritize? How do we choose what kind of consumers we will have in the municipality? And how do we ensure that we have enough power for example, new businesses and so on? Yes, next slide, please. Yeah, so this brings me to the scenarios in ORION. We have this pilot area that we are looking at. So here we are in this project developing advanced models for this kind of optimization. So the scenarios we have developed together are quite simple, I think. We have a situation today with a certain number of traffic and shore power. And we have just started this development in these areas that I showed. And then in 2035, we can define a base case of maybe the same traffic, the same 100% charging rate of shore power, and then these completely developed areas. And then we can look at, do we have enough power? Do we have the right energy mix? How can we change this and view it in the graphical digital twin? And will this improve decision support for the municipality? These are the scenarios we are working on in this project, and these are very fundamental. So this kind of models and decision support tools is really really useful for the municipality, I think, and something quite new. I think that's one final slide. Next one, please. Yeah, no, one more. The potential of digital twins. We have followed this development for several years, and we have tested a lot of different tools and use cases, but we now see that the technology is there where you can actually use these tools through web browsers, for example. So we now have included the models of some of our buildings at this test site, and we see that when we can use these models with users, we find a lot of small use cases, and we find them very, very useful. So the technology is now there where the threshold to getting started is low enough, so we can get a quite high use in the municipality, which is great. So the example on the left is for a building. It's very technical, but our ambition in this project is to sort of lift up to the area, not just single buildings, and have decision support on this whole pilot site. So this is quite exciting. So we are very enthusiastic and positive about this potential. I think that was my last one, Scott. Yes, thank you very much, and I will happily answer questions in the Q&A. Thank you.
Thank you, Andreas. So next we have a speaker from our sister project, Professor Juan. You can take the control of the screen and then you can move your slides.
That's perfect, yes. Thank you. Okay. Let me see if I can see. It's okay. We move. You cannot hear me. Someone say that.
Yeah,
Yes.
it's moving.
Can you hear me well?
Yes.
Okay. Because I read in the chat someone they said that he cannot. Okay. My name is Juan Manuel Escaño. I work for the University of Seville. I want to talk a little bit what we are doing in the Interest project from our side, no, from University of Seville, no, in this project here. But I want to focus on the idea of the twinning, because everyone is talking nowadays about digital twin, but the twinning is something crucial for the digital twin. If we don't have a connection between the real system and the twin, the digital twin model, we don't have a digital twin. We can have a model, we can have a shadow or whatever, no? But it's very important, the twinning, and the twinning perhaps decide also the way in which we model in the system, no? So Interest project has the objective to developing a hierarchical distributed model predictive control is the objective of the project for real-time monitoring and energy management of a renewable energy system. No? With also we model healthy status in other things, not just behavior or performance, no, of the system. And the objective is the control based on models. So let me change this. How we work is in this way. We use from our library, we have been modeling long time because our group is a very strong group in model predictive control, and we have a lot of models, and also we have a library, you know, for many things like fuel cells, fuel tank, electrolyzer, etc. We transfer to FMU standard way, but the most important thing is to have the real world data and to have a module to update the project to get the best matching between the reality and the digital part or counterpart. Okay, let's see some case studies that we are working now. For example, an electrolyzer, we are based in equation. Okay, is the first approach that we use is equations, physical equations. We know the system, we model the system based on equation. For example, we have the electrolyzer, and the electrolyzer has an inlet water. We use the pumping and to put the water into the membrane, and we separate by electrolysis. We separate in hydrogen and oxygen. We use also separators, you know, in both sides, you know, to get more gas, right, from the initial separation. And then we want to get, for example, the performance of the system in terms of the production of hydrogen based on the current that we put into the electrolyzer. But also we need to have a thermal model, because the temperature is something crucial for the electrolyzer. We cannot have greater temperature than a value to avoid the degradation of the membrane. In this case, for example, we separate the equation from the thermal model and the electrochemical model but after the updating based on the real data, and we can do that in real time or offline, we can have a very good validation of the model. And then we will need that updating sometimes. When the system is working for a time, we use some criteria for that. But the problem is when we don't have enough information from the real system. For example, in this case, we have an AUGM technology, for electrolyzer, and the manufacturer does not provide internal dynamics, the thermal controller and performance, or data from the controller, the logic of the fan, or any other internal parameter. What's the problem then? That with the real data, it's very difficult sometimes to match the digital twin with the physical counterpart. So in this case, we like and we use another kind, or many people use, for example, neural network or this kind of model based on data. We use neural network as well, but we prefer sometimes to use a neurofuzzy systems. Why? Because neural network at the end is a very old, it's an artificial intelligence, both of them are artificial intelligence techniques. And a neural network is a black box. And we don't know, when the neural network is trained, we don't know the information inside. It's a black box. While the neurofuzzy system is also a neural network, but we can see information inside. We can see information based on rules, not in equation, but based on rules. Those rules, even with partial information or information with uncertainties, we can get the proper information, and then we need just to fit. In this case, for example, everyone knows that picture, and the information is not accurate, but we know the picture. We know which is that painting. That's a reason which we like to use neurofuzzy system. So in this case, for example, the AUGM electrolyzer, you can see on green after the twinning using the equation, physical equation, but we don't have enough information. But on blue, I think it's on blue, no, on orange, we can see the neurofuzzy results model. No? And the good thing of that is not just that sometimes we can get better models, it's the twinning process. Because in this case, for example, we get better results. You can see the R square and the error between the model and the real data. And also the deviation is much less. But also we can see, for example, in this case, there are some numbers here. It's a time that we need to update to get the twinning. And for example, a model based on equation, this ODE, we need almost 12 minutes here. But with the neurofuzzy, we have just half a minute. Here, perhaps it's not too relevant. But for example, in other cases like this, for example, we have another object, another physical system that we have is the Fresnel collector that we have in our labs here. And the model based on equation has a lot of equation. We have to cut the tube. This is a tube in which we concentrate the solar, the sun, to produce heat. In this case, we use water, and we use that heat to produce air conditioning in the building. But for any other solar plant, we need that source of heat. And if we want to model the temperature, we have to cut in many pieces the tube, and we establish a set of equations per each piece. And then we need a lot of equation to run this. While with a fuzzy system, is quite fast. In this case, for example, we can have similar accuracy between the two kind of model, but for example, for this solar plant, the equation-based model is a lot. It's 13 hours to get a twinning, but the neurofuzzy is just 20 minutes, more or less. So on the night, we can make the twinning easily with the neurofuzzy system, but we need more than one night to get the updating and the training for this. Another kind of things that we are doing at the end is also another techniques that we use is techniques to know when we need the training, because we don't need to have in real time continuously the digital twin and the physical content part. So we have developed a techniques to know when we need to update the system. At the end, we check continuously the data from one part and the other, and with a techniques based in neural network and neurophysics, we decide when. And we have it's very long to explain here, and there are articles about that are written already. And then we can provide to the learning system the moment. So we provide the instant of updating to say now is the moment to update. Okay, this is something that we are doing here. So as a conclusion, just to say that the optimal twinning is a design choice. The thing is to choose the minimum model complexity that satisfies our control requirements and data availability. That's the idea. And you have here also my contact detail, and I will be very happy to answer the Q&A question. Thank you.
Thank you, Professor. Now we can have the questioning session. So if you have any questions, you can drop it in the chat box. I will give you a minute to type out your questions if you all have any. We have a question for Andreas. It says, which KPIs have proven most valuable for supporting operational and investment decisions in your digital twin environment?
That it depends a little bit. I'm not sure if that's only related to this project or earlier project. I'm not the very yeah. I can start by saying that the municipalities do almost everything. so it's a very wide question, but related to these specific things like infrastructure and so on. I would have to say what we are looking at in this project, it's energy demand. It's very basic actually, but you would be surprised that this is not something that a municipality is using in a strategy actively. So actually, this is something this project is introducing. So it's I know it sounds strange, but this is something new in Norway, that we are actually seeing energy as a limited resource. So I would say that's the most important thing in this project. And then where the potential really lies in municipalities in general is maybe energy effectivization, or like we have the most buildings usually, so any potential for energy savings is really important, and that's something that is not looked at enough, in my opinion. So I hope that's kind of an answer. Thank you.
So we'll be having our next webinar session on next Monday. And if you have not registered, you can register or share the link with whoever you think will benefit from this next session. Thank you, everyone. I really appreciated everybody who have joined today, and speakers who have delivered like such an amazing information. We hope to see you for the next session on next Monday. As I said, do follow us on LinkedIn. There'll be more updates about speakers and about the next session. And yeah, have a nice day. And thank you once again. Okay.